Hello and welcome to our talk for the Adaptive and Learning Agents workshop. Our paper is entitled Dominance Criteria and Solution Sets for the Expected Scalarized Returns. This paper is by Conor, Timothy, Diederik, Enda, and Patrick. So a brief introduction. When a user's preferences over objectives or a utility function are unknown, multi-objective reinforcement learning methods must be used to learn a set of optimal solutions. Under the Expected Scalarized Returns criterion, a set of optimal solutions has yet to be defined. And under the ESR criterion, or expected scalarized returns criterion, we must consider a distribution over the returns when learning policies. And therefore, to learn a set of optimal solutions, we propose using first-order stochastic dominance to define a partial ordering over policies under the ESR criterion, and therefore we can define a set of optimal policies. So some background. First, we'll cover multi-objective reinforcement learning, then we'll look at some utility functions and what they are, and then we'll look at the scalarized expected returns criterion and the expected scalarized returns criterion. And finally, we'll look at the method that we use to determine a set of optimal policies under the ESR criterion, stochastic dominance. So what is multi-objective reinforcement learning? Multi-objective reinforcement learning is a natural extension to single objective reinforcement learning, except we just consider decision problems with multiple objectives. And instead of a Markov decision process, we consider a multi-objective Markov decision process, or MOMDP, where R is the rewards are n-dimensional vectors, where n is the number of objectives. So various scenarios exist depending on the availability of the user's utility function. If we are in the unknown utility function scenario, where the utility function of the user is unknown at the time of learning or planning, then we must use a multi-policy method to learn a set of optimal solutions and return those back to the user. And of course, the user's utility function represents the user's preferences over objectives. And under multi-objective reinforcement learning, there are two optimality criteria: the scalarized expected returns and the expected scalarized returns. So utility functions. Linear utility functions are the most widely used to represent a user's preferences, where we can see here that Wi is the preference weight for objective I, and Ri is the objective value of the return vector, and we just multiply those together for all I, and we get a utility back. Unfortunately, if the user's utility function is nonlinear, then we cannot represent the user's preferences over objectives as a linear utility function. We'll end up learning a suboptimal policy. So to overcome this, we consider monotonically increasing utility functions. And we can see here from the equation how we can define that the utility is greater for a value of pi is greater than the utility for a value of pi prime, basically if for all objectives or for all I, that the value at that index of the vector is greater than or equal to for all of the objectives, and then for at least one that it's greater than, we can say that the utility of v pi is greater than v pi prime. And fortunately, monotonically increasing utility functions include both linear and nonlinear utility functions. And now we'll just talk about the two optimality criteria under multi-objective reinforcement learning. We have the scalarized expected returns, or SER, and this is the most commonly used optimality criterion in multi-objective reinforcement learning, where the utility of a user is derived from multiple executions of a policy. That means the user will basically have multiple opportunities to execute that policy. And to compute that, we first calculate the expectation vector, and then we just apply the utility function to get our scalar value. And the expected scalarized returns, or ESR, has largely been ignored by the multi-objective RL community. And in this case, the utility of a user is derived from the single execution of a policy. So that means the user will have only one opportunity to execute this policy. And for an example of this, we can consider a medical setting where a patient who has an illness may only have one opportunity to treat that illness. And to calculate the ESR criterion, we apply the utility function to the return vector, and then we compute the expectation. And of course, for nonlinear utility functions, the policies learned under the ESR and the SER criteria are the same. Basically, there is no distinction between the two. But for nonlinear utility functions, the policies learned under ESR and SER are different, and they can be significantly different. And this is problematic because in the real world, utility functions can be nonlinear. So if we use an SER method to learn a policy where we should be using an ESR method, we'll end up learning I suppose, a suboptimal policy, essentially. And we'll see that later on. Next, we'll just talk briefly about stochastic dominance, and stochastic dominance gives a partial ordering over distributions. And since we're using a distribution under the ESR criterion, this is a perfect kind of method that we can use to determine, I suppose, preferences over policies when the utility function of a user is unknown. So this is, as I said, incredibly useful when a distribution must be taken into consideration instead of the expected value, which is exactly what we're trying to do under the ESR criterion. And we focus on first order stochastic dominance. And we can see here how stochastic dominance is defined in terms of the PDF and, of course, in terms of the CDF for two random variables, x and y. So as I mentioned previously, for nonlinear utility functions, the policies learned under ESR and SER can be different. So let's consider this a following example where we have lottery 1 and lottery 2. And our utility function here is nonlinear. And as you can see, under SER, the agent will prefer lottery 1. Lottery 1 has a value of 9.5, and lottery 2 has a value of 9.14. And then under ESR, the agent will prefer lottery 2, as lottery 2 has a value of 19.4, and lottery 1 has a value of 19. I'm not going to go in depth into the mathematics here, but as you can see, you can go through that yourselves. Pause the video now if you'd like to just get a better idea of how this all works. But you can see that the under SER we'll prefer lottery 1, and under ESR we'll prefer lottery 2, and that can have implications in a larger sequential decision-making problem. And recently, Hayes et al. Have shown that a distribution of the returns is required to learn optimal policies under the ESR criterion. And to understand why, let's first of all consider when the utility function of a user is unknown. If we were to compute the expectation vector, which is all that we would be able to do underneath when the utility function is unknown, then we would no longer be optimizing under the ESR criterion. We'd actually be doing SER, and that completely is invalid. So that's number one. And number two is if we look at lottery 3 and lottery 4, where this utility function, both lotteries have the same expected value of 5. But both have significantly different outcomes. So we propose that if we're trying to maximize our utility, and we, I guess, only have one opportunity to execute the policy in the real world, we're learning a policy where we will only have one opportunity to execute that, then we better make decisions not on the expected value, but more on the distribution, as it'll give us more information that's required to actually maximize utility instead of like the utility of the expectation, I guess. And in this case, the current multi-objective ORA literature on the ESR criterion only assumes a scalar expected utility, and this is just not sufficient to exploit positive outcomes and avoid negative outcomes that a decision may have. So to overcome this, we define the multi-objective version of the value distribution, and the value distribution was defined by Belmer et al. In their distributional perspective on reinforcement learning paper. Where Z pi is the distribution over the returns of a random vector when a policy pi is executed. And then we can use this value distribution to learn a set of optimal policies for the ESR criterion. So we briefly talked about stochastic dominance earlier, and now we're going to kind of incorporate that with the new value distribution that we've just introduced to learn a set of optimal policies for the expected scalarized returns. So in the paper, we show that first order stochastic dominance can be used to give a partial ordering over random vectors. And you can see how a random vector x, will first order stochastic dominate a random vector y for all monotonically increasing utility functions, and we can see that here. And that's based on the definition of stochastic dominance that we introduced earlier. And it just says that the probability that the utility of x is greater than the utility of v is greater than the probability that utility of y is greater than the utility of v for all v. And remember here that u is monotonically increasing. And we also prove that for random vectors x and y, that the expected utility of x is greater than the expected utility of y if FSD, or first order stochastically, dominates y. And that's very important when we're optimizing under the ESR criterion. And therefore, since this is true, we can then extend that then to the value distribution. Then we can say that Z pi, first order stochastic dominates Z pi prime, then we will always prefer Z pi. And then we have a partial ordering over policies under the ESR criterion. And now we'll quickly define some of the sets, and we can use the definition that we just introduced. And the undominated set is a subset of all possible policies for where there exists some utility function u that is monotonically increasing, where a policy's value distribution is first order stochastically dominant. And we can see what the undominated set is there. And the coverage set is a subset of the undominated set, where for every utility function u that is monotonically increasing, the set contains a policy that has a first order stochastically dominant value distribution. And we can see that then again for CS here. And then using FSD to determine an optimal set of policies is difficult because first order stochastic dominance relies on having the utility function of the user available. So this obviously has limitations when we're actually trying to do this in practice when we don't know the utility function of the user. And so to overcome this limitation, we define ESR dominance. And ESR dominance has an extra kind of criteria here where we require one of the I guess V's to be the probability of that for X to be greater than the probability of that occurring in Y. And this just makes sure that we don't have duplicates in the sets. And this just is used in practice. And this is important in practice. So we haven't really we've made quite a jump here. If you go to the actual paper itself, you'll be able to see the transition. It's much more smooth, but because it's just a quick presentation, I'll just have to jump ahead. So we can see here with ESR dominance that this also holds for random vectors. And therefore, we can extend that to value distributions. But first, what we do is we just introduce predominance. And we can say that basically that if X predominates V, and the probability of that is greater than the probability of Y predominating V for all V, and that there exists some V where the probability of X predominating V is greater than the probability of Y predominates V, then we can say X ESR dominates Y. And that removes then the need to compute utility, and we can actually use this then in the unknown utility function scenario to give to learn a set. And then we can say then that we have two policies or value distributions that represent policies Z pi and Z pi prime, and that we prefer Z pi if Z pi ESR dominates Z pi prime. And using ESR dominance, then it's possible to define a set of optimal policies known as the ESR set, which we can see below. And in the ESR set, there are no duplicate policies. Again, if you want further information on this set, please refer back to the full paper. And the conclusion then, this work has defined the necessary notation for the value distribution for the ESR criterion. As we showed in or talked about in the presentation, that before we were operating off of a single scalar, that's not sufficient. And we've actually now introduced a distribution that we can use to represent policies under the ESR criterion. And we also define multiple solution sets which prior to this work did not exist. So now there is actually a kind of a framework there where we can now start implementing algorithms to learn these sets and actually satisfy the ESR criterion when the utility function of a user is unknown. And yeah, basically the solution sets defined can now be used, as I've already said, to learn an optimal set of policies in multi-objective RL when the utility of the function of the user is unknown. And this has, I guess, a lot of implications in multi-objective RL because we can now consider scenarios which before this we could not consider, or consider them correctly anyway. Future work then, we aim to define a multi-objective RL algorithm that can learn the ESR set, first of all in a bandit setting, which is a kind of a much more simpler setting, and we can kind of really test out a lot of these theories in practice there, and then we can extend them to a multi-objective Markov decision process and learn them for real-world scenarios eventually at some point in the future. We also hope that this work inspires more research into the area of ESR. As I've already mentioned, this area has been really ignored and really understudied, and it really lacks like sufficient benchmarks, metrics, and the algorithms. There are only a few algorithms in existence at the moment that can learn policies under the ESR criterion, and we hope that this kind of work will encourage people to maybe take a new direction and maybe focus on this criterion. And then I suppose on this final note, I'd like to just leave you on this. In order to fully deploy multi-objective reinforcement learning algorithms in the real world, the multi-objective RL community needs to consider the ESR criterion. And I've highlighted this throughout the paper, but basically, in scenarios where we only have one opportunity to execute a policy, we must consider the ESR criterion. And if we don't, then we're going to use SER methods to learn a policy for something that should be, I suppose, optimized for the ESR, and that'll lead to suboptimal performance, which is not acceptable in the real world. So we really need to consider this as a community, and hopefully this paper can really inspire people to look into this further. So that's it. If anybody has any questions, please feel free to message on the Slack channel, or please feel free to email me. Either or is perfect, but hopefully during the course of ALA we can get a good conversation going on the Slack channel. So thank you very much, and yep, thanks.